Just seen how obnoxious it is to actually try to evaluate the derivative of anything using the definition. We would now like to see if we can't develop a collection of shortcuts, and that's pretty much what the rest of this whole video series is devoted toward, is getting shortcuts, or even what isn't necessarily shortcuts, truly getting certain derivatives that are really, really hard to get. And we'll just kind of state what the conclusions are. Although I do give a lot of proofs. So anyway, to get into it, we have already seen in the exercises that basically x to the 0, which is 1, its derivative is equal to 0. And we didn't exactly see that. We saw that the derivative of 2 was equal to 0. But you could repeat the proof and see that the derivative of 1 is equal to 0. The proof will go the same way. We've also seen that the derivative of x is equal to 1. Again, I don't think we actually showed that exactly so, but we did look at, I think, 2x minus 1, and the proof that we used for that would apply just as well for talking about x, or x to the 1. And we also saw that the derivative of x squared is 2x, and we also saw that the derivative of x cubed was 3x squared. And at this point, it's starting to look like a pattern. I kind of probably should have arranged these in ascending order, but they all seem to follow this formula, that you take the exponent, move it down, and subtract the exponent by 1. In this case, well, if you move 0 down, you don't even have to think anymore. Now you're multiplying by 0, so it's just 0. So that seems to conform to this formula. Here, if you move 1 down and take instead x to the 0, right? Subtracting 1 off of the exponent. Now you've got 1 times 1, which is equal to 1. So even these cases, which didn't obviously conform to the rule that I'm pointing out here, it turns out that if you think about them in the right way, they do conform to this rule down here. Clearly, this one's even easier to see because you drop the 2 down in front, you subtract 1 off of the exponent, x to the 1 is x. So even in this case, the rule even more obviously applies, and then here it's just completely obvious how the rule applies. So it's reasonable to think that this applies for all possible values of n. Now, I'm going to give a proof. If you don't care about proofs, then really all you have to know is the rule, right? Here's the rule in orange. It's called the power rule. And this is what you really need to know for, getting the sort of basics of the calculus lesson. But I'm going to go ahead and give a proof because I think the proofs are good little mental exercises and help you to work with the concepts and do, increasingly abstract mathematics. So I'll give the proof, but if you're not interested, you can skip it. Okay. The proof makes use of what's called the binomial theorem. You might have seen this in high school, or you might not. If you were in a fairly advanced high school class, you'd see this, but if your high school class was not that advanced, then it may look completely new to you. But if I get to use it, then the proof becomes quite easy. Well, at least somewhat easy. Sure looks ugly, especially in this neighborhood, but it does make the proof a little bit nicer than it would otherwise be if I didn't have access to it. So let's go ahead and start into the proof. I am thinking about x to the n, right? So right now what I'm really looking for is the derivative of x to the n, right? F of x equals x to the n. That's what I'm talking about. So here I have x to the n. Here I have x minus h to the n. And if you look at this piece, it lines up with the binomial theorem. So that's where the binomial theorem is helpful, is that I take this and I turn it into the binomial theorem's thing, basically. Except that in jumping from here to here, I've actually done an extra step on top of just replacing it with the binomial theorem. I've also noticed that if you plug in n, right, if you can read the summation notation, I'll explain it. It says first plug in 0, then plug in 1, then plug in 2, so on until you plug in n as the last thing that you plug in for I, right? You're always plugging in for I, right? So if you plug in 0, you'll get n choose 0 is equal to 1. If you're not familiar with the choose function, that takes a little, that's a little bit too much of a distraction, so I'm not going to discuss it. But you get n choose 0, which is equal to 1. And then you get n, let's talk about the first term. So n choose 0 is 1. A to the 0 is 1, and then b to the n minus 0 is just b to the n. And that kind of makes sense, because we know that whenever we multiply these things out, you get b to the n eventually, right? You initially get a to the n, and then then you get all these more complicated, obnoxious terms. And then at the very end, it looks like you get b to the n every time you do one of these things. So that makes sense. That we see that term coming out when we plug in 0 for I, is you get 1 times b to the n, just as we tend to expect. So that makes good sense. And also when you plug in n, right? That's at the other end of this process. The very last thing that you do is plug in n, and then you get n choose n, which is also equal to 1, and you get a to the n, b to the 0. B to the 0 is 1. So ultimately, the very last term will be a to the n in this case. And we know that that tends to happen when we multiply things like this out. So what I've done is I know that in this case, when I line these things up, instead of talking about a, I'm really talking about x, and instead of talking about b, I'm really talking about minus h. So I know that one of these terms, the very last one, right, by plugging in n, the very last one will get me x to the n, and it'll cancel with this x to the n. So I've gone ahead and done the cancellation already. In doing so, I am peeling off the last term, right? I don't need the sum from 0 to n anymore. I've already split off that nth term. So really, I only sum from 0 up to n minus 1. And in doing so, I've kind of, this negative here is just kind of hanging on over here. So this is the result, right? So after replacing this with the binomial theorem and canceling that one term, I get this. Now from here, what I'd like to do is remark that if you plug in n minus 1 into the remaining thing, you'll get n choose n minus 1. That's here. I'm splitting off that last term again, right? So n choose n minus 1 is here. Then I'll have x to the n minus 1, because again, I'm plugging in n minus 1 for I. And then I'll get negative h to the n minus 1. And if you do the appropriate calculations, then you will get that that is equal to just negative h to the 1. I cancel the negatives. That's why there's no negative sign on this term, is because I've taken this negative together with the negative that comes from negative h. I've canceled them in this term. And, oops. And then I've got an h on top and I've got an h on bottom, so I cancel the h's and I get this, right? So after splitting off the n minus 1 term, this term results. And everywhere else, I just divide by h, which really just means putting an extra minus 1 in the exponent of this over here. Now, at this point, the important thing to remark is that this does not have h in it. So it stays after we take the limit. But everything else is going to have an h in it. So this all just vanishes, turns into 0. And the only thing we're left with is this right here. And surprise, surprise, n choose n minus 1, it is possible to prove it's just equal to n. This is exactly the result that we thought we would get. So there's the proof.